Welcome to this video. In this video we will talk about noise in op-amp circuits. And this is meant actually to be a fairly rudimentary introduction. This is a topic in which you can spend a lot of time, cover a lot of ground. But we're going to look at some very basic analysis that is useful, at least when you're beginning to do a design. Quite often you'll want to be much more detailed and more careful about how you do the analysis, but this gives you at least a starting point to see if your ideas make sense. Okay, and to do this introduction to noise in op-amp circuits, we will use this non-inverting op-amp configuration. The reason is that this will make a good example and it will hopefully introduce the ideas that we need to talk about. So the idea is that resistors and the op-amp itself are actually sources of noise. Resistors are sources of thermal noise, and the op-amp is a source of thermal noise, shot noise, and flicker noise. So we have to figure out how to model these noise sources. And typically the way we do this with resistors is to take a real live resistor, something like this in a circuit, and model it as a noise source, which models the thermal noise generated by the resistor, and then a noiseless resistor. Now, you just have to keep track of which type of model we're using because there's not a separate type of symbol for a noiseless resistor. Okay, we know that the voltage produced by this resistor, which in this case we might call V1, is given by the square root of 4kT BR1. Okay, where K is Boltzmann's constant, T is temp, or the temperature, in degrees Kelvin, and B is the system bandwidth. System bandwidth. There. Okay, in hertz. And so if I know the temperature, and I know the resistance, and I know the system bandwidth, then I can tell you what the RMS noise voltage is going to be generated by this resistor. Now it's important to note that this is an RMS voltage. We don't know what the actual voltage is going to be at any given time because it's noise. But what we do know is that on average the noise will have a certain power, and that power is equivalent to a given RMS voltage. So this is the equivalent circuit or representation of a resistor. Now we can also have equivalent representations of op-amps and their noise. Most of the time we'll use what's called an input referred noise model. And the idea is that this real op-amp that's got noise and stuff everywhere will be represented by an input or a voltage source, which we might call V sub n, connected to the non-inverting input of the op-amp, and then and then a noiseless op-amp here. Okay, now this is actually probably the simplest noise model for an op-amp. There's much more complex noise models. Or quite often you will see noise models including both input referred voltage sources connected as we have it connected here, and then input referred current sources, one for the non-inverting input and one for the inverting input. Quite often these noise sources are also a function of frequency. And this depends on the way the op-amp is constructed, how this function of frequency would look. But this is the approach we'll use. It's probably the simplest one. It has the advantage that quite often the noise value for the op-amp is given in a spec sheet in terms of, you'll quite often see it be something like, say, 25 nanovolts per square root hertz. And again, this is something given in a spec sheet. So to actually get Vn, you take this noise specification and you multiply it by the square root of the system bandwidth. And that gives you then a voltage. Again, this is an RMS voltage because this is a noise. At any given time, we don't know exactly what the value is. We just know its average power, and from that we can get an RMS voltage. So that's pretty much the approach that we will use. And I think at this point I will stop this video. This will be part 1. And in part 2, we will actually use these models that include noise sources to do the analysis inside, or do the analysis of this non-inverting op-amp circuit. So stay tuned for the next video.